עכשיו נהרס מהרב.
Okay, you are with me?
Yes.
Yes. Okay. So, hi everyone today. Let's see. So we started last week to explore different parameters in the scattering process, if you remember. We discussed the scattering amplitude, scattering intensity, the cross-section, the optical theorem, if you remember all this concept. Okay, so we tried to describe, to have some formulation, some description of the scattering by particle, any type of particle. Okay. So today I'm going to take a different direction. Okay. Based on an analogy, we discussed actually that analogy last time, we mentioned that. So today we are going to talk about the electromagnetic radiation theory applied to the problem of scattering. And actually this theory is very powerful. It is used to treat actually a complex scattering system in the far field when you are far from the scattering area, the scattering volume. And I just want really to present the basics, the concepts, okay? We don't have time to go into detail to demonstrate everything, and also it's boring, okay? So I try to do it as light as possible, but okay, be with me today. Okay. So, if you remember, last time we discussed the scattering pattern by a particle. We saw this diagram here, so you have light coming from here, and we look at the diagram in the far field, how the light is scattered with which amplitude in different direction, different type of scatterers. Okay, so that's typical of a scattering diagram or a scattering pattern. Okay, and you remember we mentioned the analogy with an antenna. Okay, or a horn here, a horn antenna. Okay, actually you find the same type of pattern, which is shown here. So if you want to look at the emission of your antenna, you can describe the antenna radiation pattern here, which has several lobes in the forward direction, in the backward direction. Okay, so this is very similar. I mean, these two descriptions are actually quite similar. So the radiation pattern describes how the antenna radiates outward, far from the antenna. And the scattering diagram shows how a scatterer or any type of object will scatter light in different directions. Okay. So actually, it's not just an analogy. Actually, the things are similar or even identical. And this is based on the theory that we are going to describe today. And the idea is like that, is that when you have an electromagnetic wave incident on some scatterer, on some object, then it will generate some movement inside this volume. Okay, so for instance, if you have an atom, okay, with a nucleus and the electronic cloud around, if the electromagnetic wave comes and impinges on this object, the electric field will displace the electron or the electron cloud away from the center here, from the nucleus, back and forth around the nucleus. Okay, so this can be actually described very simply with two charges. Okay, and the distance between these two charges oscillates in time. Okay. And you can define the dipole moment, which is this vector P of t, which is the charge times the distance between the two objects, okay, the plus and the minus charges in the system. Okay. So the wave comes, it excites the atom here, the system starts to oscillate. And what happens when you have a dipole moment? Then you have also a current that will generate a current, and the current will also radiate a new field. Okay. So this particle movement induces a time-dependent current, which in turn radiates an electromagnetic field. Okay. So we have wave coming, exciting the system in turn radiates back the energy, the wave, from the oscillation of the dipole. Okay. So you see that calculating the scattering by a particle is equivalent to calculate the emission by a dipole in that particular case. Okay.
So the induced current by the dipole, it can be described like the induced current of the dipole.
Yes, so the dipole oscillates, generates a local current. Okay, which are related here. Just briefly the relation between the two. Okay, and this current, like any dipole that oscillates, will radiate a wave. So here we are looking closer at the interaction between light and matter, wave and matter, what we didn't do last time. Okay, last time we were just ignoring what was going on there, and we were looking at the far field. So here, by looking closer inside the system at the interaction between light and matter, we can actually model the problem by the re-emission of waves by dipoles. Okay. So calculating the scattered field will amount actually to calculate the field emitted by radiated by the induced current by the dipole. So there is a clear similarity between the scattering, like we see before, the scattering diagram and the radiation pattern of the antenna. So this particle movement induced, okay, that's how I said it. So here, what is interesting is because of the linearity of the wave of the Maxwell equation, any field, electric field or magnetic field, okay, will be proportional. Actually, the radiated field from the antenna is just proportional to this current, this current density actually, okay. And this gives you a full description of how the field radiates from the particle, so how the field is scattered by the particle. Okay, so we don't see anything here. So this is so calculating the scattered field is equivalent to calculating the field radiated by the induced current. So this is the theory of electromagnetic radiation that we are going to develop to be able to calculate the radiation by particle, the scattering by particle. Okay, so the analogy is clear. Okay.
No,
not clear.
No, not so much.
Okay, so you have a field that comes and is scattered by a particle, okay, and the field is scattered in different directions. Okay, you can describe the physics there in the particle by an interaction between the wave.
In all the particles, not the positive particle.
Yeah, I mean any atom or molecule, whatever, okay, will actually be excited by the field. The field will displace the charges one from the other, oscillating, okay. And this oscillation by definition is the dipole. And the dipole radiates another field, okay? Actually at the same frequency as the incident field itself, okay, in that case. Okay. So actually this simple model is used, this is not part of this chapter, but I wanted to mention to you the Lorentz model. Are you familiar with that? This is used actually to describe the laser. Laser physics can be based actually on a semi-classical description of light. Okay, and in this model, Lorentz actually described the dipole here as simply a pair here of two masses linked by a spring. Okay. And the spring equation is given by that.
Yes.
Okay.
So what it means over
yeah, I
the
wanted
term?
to ask because it's exactly like the same as spring potential. No.
Yes. So from
Power.
here.
Yes. Spring power. Like this part of the equation. The first part.
Yeah.
No, the other one.
This part.
This part.
So this is the the spring constant. Okay. That describe how the object. The particle or the object moves with the spring. Okay, so this is the basic equation here of motion. Okay, there is a term here which that's the oscillation. There's the damping term, okay? You imagine that there is some damping, some
friction.
attenuation.
It's like friction.
Yeah, friction in that case, yes. And some source term here if you excite the system, okay?
If you're what?
If you excite the system, if you move it, okay, so you have a source, okay? And actually you can replace those parameters by those one here, just by stating that omega square is k over m, okay, that's the oscillation, the angular frequency of the oscillation, okay? And the trick of the Lorentz model is to say, okay, this is exactly the frequency of the wave that will be emitted by this oscillation object here, electron and
Yes, in the
nucleus.
default.
Yeah. So that's really a shortcut, okay? But it's very nice actually. This is used to describe very nicely the physics of light matter interaction, especially in lasers when you want to discuss the interaction with the atomic structure. But this is not the point. I just wanted to mention that to you. I think it's interesting. So omega, so actually the actual resonance includes the omega 0 and also the damping term here. I mean, you have all the physics is there. The gamma, the term here, which is the damping term, the decaying term, is related to the decay due to radiation and non-additive transfer. I mean, all the physics can be described with this simple model. And you get this kind of damping oscillation. Okay, but that was not okay. Forget about that. That's just I like this model because you can really sense it. Okay, so let's go now back to our theory of electromagnetic radiation and give the outline. We will see essentially two concepts. First one is the concept of retardated potentials. The other one is Green function. Are you familiar with that? Who knows about retardated potentials? Who learned about that already?
We learned it
That's about many years ago.
2 years ago.
2 years ago.
For me, 2 years ago.
Yes, so you know about that. So what we have. Are you familiar with that? Retardated potentials? Not really. Okay. So I will try to explain slowly. And the second concept is green function. This is a very powerful tool that is used everywhere. So I think it's good to learn a little bit about that.
But the green function we learn on Memphis as well.
You learned it also?
Memphis courses.
Advanced mathematics.
Advanced mathematics. I don't know why.
Okay, good. So we'll talk about that. This tool is very useful for the next courses where we will deal with multiple scattering. Okay, we can use a recursive green function actually to calculate multiple scattering in the system. Okay, but for now will be very simple. I will give you the green function in free space. But the idea is to go over this different concept and try to understand and to get some feelings about that. Okay, so what about rotated potentials? So the rotated potentials, are you familiar with vector potential? Yes, the A, okay? Yeah. The A, the V is the potential, the scalar potential, and A is the vector potential, okay? So that's actually what we are going to deal with, okay? So simply that. So the rotated potentials here, so they are actually the vector potential corresponding to the electromagnetic wave that we are going to consider, okay, that are generated by these moving charges, okay, those dipoles that emit the electromagnetic wave, okay. So we'll see that actually the knowledge of this potential, this vector potential, away far from the particle is enough to describe the field, the electric magnetic field. You can describe all the waves with this simple concept. Okay, so this is really a crucial concept developed in electromagnetism. So we'll see how we describe actually the emission by a charge. So I just want to give a quick reminders here. So, things I'm sure you know. So you remember that when you consider electrostatic fields, means field without time variation. Okay, so you can you know that the if field is conservative, is rotationally 0. If you are not familiar with some notation, you tell me. Okay. So that means that you can define a scalar potential, which is a scalar field, which gradient here is minus the gradient actually is the E field, the electric field of the electromagnetic wave, so for the electrostatic case. Okay, so E is minus the gradient of V. Okay, but that's the case of electrostatic physics. Okay, now if you go to electrodynamics, that means that now you have time playing a role. Okay, so this is not true anymore. Actually, the rotational of E is minus dB over dt. Okay, that's from the Maxwell relation, so it's not equal to 0, so it's not anymore conservative. So the field itself needs another vector here to be described, which is so minus gradient of V is maintained minus dA over dt, where A is called the vector potential. Okay, and the vector potential actually is defined from the B field, from the magnetic field. Okay, B is equal to rotational of A. Okay, different notation. Maybe you are more used to curl, no? More curl than rotational. Yeah,
Curl.
Or these notations.
Yeah.
Okay. You know all of it. So most of the time I will say I will write it like that. So you have to realize that the vector potential is a vector field whose curl or whose rotational is B, and B is a solenoidal vector field. You know what is a solenoidal vector field? That's the solenoid.
Yes.
Okay. So
It's like a spring that is closed, right?
that's the definition of a solenoid. But what do we mean by solenoidal vector field? That's
it's equal 0, like the electromagnetic inside. No.
So the idea is, you know, when you take a magnet, plus minus, take a bar, magnetic bar, okay? If you cut it, do you have a plus and a
No,
minus?
you don't have. It's
You have plus minus and plus minus. Okay?
that's right.
So you cannot have charge that are isolated. There is no magnetic charge which is isolated. You have only magnetic dipoles, never magnetic charge. As opposed to the electric field, which has electric, like electrons
That's
or
the
protons,
multiple.
plus or minus. Yeah. So the idea is that I mean, this is specific to B. Like the field, the magnetic field never ends to a point. Okay, it's always parallel lines that goes in cycle. Okay, and when you have this solenoid, okay, it creates a B field which is parallel inside and goes around and back inside. Okay, so that's the idea of the solenoidal vector field. But what we have to remember is that, okay, so B is A is defined as the rotation of B. So this comes actually from the Maxwell equation. So that's my second reminder here. Or first, some equations, some well-known mathematical result about those operators. Are you familiar with those relations?
Yes.
So the divergence of the rotational is 0, whatever u is. Okay. The rotation of the gradient is also 0. And there is a formula here which is very useful when you work with the Maxwell equation and you want to go to the wave equation, is that the rotation of the rotational is the gradient of the divergence minus the Laplacian. Okay, so this is a different way to write it. Here also, okay, just these three formulas that will be useful for us. Okay. So Maxwell equation. The first two Maxwell equations are the Gauss equation and Maxwell-Faraday equation. So this one says that the divergence of P is equal to 0. Okay. From these, divergence of a rotational is always 0. Okay, so you can write B as a rotational. So that's the definition that we just gave. That B is the rotation of a given vector A, which is the potential, the vector potential. The vector potential. In French, it's potential vector, so mixed. Okay, and from the second equation here, if you replace, you will find that the E field is minus the gradient of A. So this is because the rotation of a gradient is 0. So if you don't have this term, you get gradient of B. Okay, and the extra term comes from this relation. Okay, so that defines the two potential, the scalar and the vector potential. So what do we do with that? So you know that a potential is defined at a constant. So you can always add a constant to V, it will be always a solution. Okay, and same for A, it is defined to a vector, to an additional vector. Okay. So if you want to force the definition of A and V, so usually what you use is a gauge. Sorry, so it's not coming now. It's coming next. I will mention that next. First, the two other Maxwell equation. Is that yes? Maybe there is a mistake here. You remember the name of the two envelopes? I'm surprised. Okay, so there is one which relates the E field.
This one is Gauss.
This one, yes.
Yes.
So it relates the E field with the density of charges, and the other one relates B, the B field, with the density of current. Okay, and it is related to the derivative of the. So those are the four standard Maxwell equations. Okay, we can write them in terms of E and B, or we can write them in terms of A and V. Okay, you can replace and get similar equation with A and V. If you do that, you come up with equations which are mixed between A and V. They are not decoupled. Okay, so you can use a special gauge here. The gauge condition. This is the Lorentz gauge condition that force this relation between A and V. Okay, with this relation, it turns out that you can decouple A and V in the Maxwell equation. And
I'm sorry. A as well as V are in potential.
So V is a scalar potential.
Scalar potential, but A is a vector potential.
Right. Okay. So A comes from B, from the B field,
yes,
and V
yes.
comes from the E field. Okay. So when you do that, when you use this gauge condition, and you can force a relation like that because all those the A and V are defined to a constant. Okay. So you can do that. When you do that, you end up with two relations that are completely decoupled. Okay, so that's the magic of this gauge here, is that you decouple, you get a wave equation for the vector potential, and you get a scalar wave equation for the scalar potential. Okay.
It's matter how we got there because I don't understand completely how we got to the.
How you get this equation?
Yeah.
So you use this relation here, and you replace them here, here and here. Okay. So by replacing those parameters and using this condition here, actually you simplify, you decouple the equation, and you get these two equations. Okay, I'll let you check it. I mean, that's very easy. Okay. Using the formula that we have here. Okay, you need to use this relation. Because here, if you replace B by rotation of, you get rotation of A, okay, and E here is this function. So by using this relation here, you end up with the wave equation. Okay, that's always how you get the wave equation,
yes.
Using the third formula up there. Okay, so that's just to review some very elementary concepts. But I mean, it's not elementary, and it's quite deep, I think. You know, when you prepare the course, you realize how deep it is. Okay. So with that, with those tools, we are able to start and to define the retarded potential that I want to use. Okay. So let's start with a volume where we have our sources, our dipoles. Okay. And we are looking far away at some distance, not far away from now, at some distance r from this object here. Okay. So we can define a current density in that volume, G of r prime t. So r prime is the coordinate inside here, and r is the coordinate outside there. So if we consider monochromatic waves, okay, so you can take out the time oscillation here.
If it's far away, I can say that the potential equals to 0.
Into infinity, yes.
Into infinity,
That's a condition that you can use as well. Okay. So here we define the current, and there the current. So the current will radiate away, okay, at the position r of an observer. So at the position r of the observer here, it will radiate an electromagnetic field, which can be characterized by its vector potential. Okay, so A of r at time t. So it's the real part of A of r, that's the amplitude, and that's the time variation, the time the phase. Okay. So the question is, can we relate A and J? Okay. So starting from this equation that we found before using the Lorentz gauge, okay, we can show that this expression here is a solution, is a fundamental solution of that equation, that wave equation of the wave vector, of the vector potential. Sorry. So the potential at position r at time t is mu0 over 4 pi. Then you need to integrate over the volume of the sources of the currents here. You integrate over the currents here J over r T3 r prime. So we integrate over that volume over all the sources that will contribute to emit to radiate toward that position r at time t. Okay. So that's something I don't demonstrate, but you can just take this and just put it in the equation there, okay, and you'll see that it's true. It will solve the equation, okay. Okay, so I define. So
it's the potential of like a single particle.
That's the vector potential of the electromagnetic field at that position, generated by all the particles of these volumes, because we integrate here over the volume. Okay?
Yeah, I know. The potential itself, like, okay, inside the integral.
Yes. Oh, this is the current here. The current density.
Yeah,
J.
divided by the R.
By R. Yeah. So what is R?
Is it constant?
No. So what is R? So R is defined as the difference R minus R prime. So you see on this picture you have, so R prime is inside the volume here, okay? The distance from R prime to this position here, okay, is R. So R is small r minus small r prime. Okay, so that's the definition of R. And you see this term here is very important here. T minus R over C. This to take into account that it takes time for light to travel from here to there. Okay, so very important to introduce the fact that speed of light is finite. Okay, and for that reason, you have to take into account the retardation, okay, the delay between the oscillation of your dipoles, okay, and the time it takes for the radiated field to reach that particular point. Okay, so this is actually defined here, introduced here by this term. So c is the speed of light, and r is the distance from the dipole to the position where we measure the field. Okay. So the retarded potential describes the effect of the field generated by a current in the past. Okay. So it's the same idea that when you look at a star in the sky, okay, what you see is the star after maybe millions of years of emission, of its initial emission. So the emission that you see is actually in the past. You are looking in the past. So the same idea here. Okay. Okay, so let's see what we can do. So now we have a relation between the vector potential and the dot current density. Okay, what can we do with that? Can we express that in a simpler way? So the first approximation is the far field approximation. Okay, to go back to what we did last week. So the idea is to consider that R is much larger than the size, the volume of the dipoles. Okay, we can add another relation here. I'm not going into detail here, and we don't see much here. Okay, so here the approximation is like that. So let's say that here exponential IKR over R. Okay, that was in the integral term. Yes. Oh, sorry, I forgot to because it's hidden here. So in the case of a monochromatic wave, okay, you can just replace J here by its amplitude J of R prime, okay, times exponential IKR over R. Exponential IKR tells you the phase accumulated along this distance R. Okay, so this T minus R over C, it comes here in the phase term IKR plus or minus I omega T here. Okay, so that's the phase term. So this term here, okay, we can actually approximate it in the far field. So the way to do that is very simple. You have so exponential IK over R. R is the amplitude. 1 over R is the amplitude. So R can be approximated by this R here, the small r. Okay, not very different. Imagine that this is very far away from that point. And the phase term here, IKR. So here we want to be a little more precise. So the R here is replaced by R minus U times R prime. So U is the unit vector along this line here. Okay. U times.
It's like to say Darkova, our head.
How you call that? R8.
Our head. Our with zero.
I don't know what you. Yeah. If it's really, I don't know what.
If you want it to be,
yeah,
it will be.
No.
You can put your hand.
Really.
Okay.
No,
so this is very simple. You see the difference. So R is R minus R prime. Okay. The difference between this distance and that distance is this small distance here. Okay. So what I write here is the projection of R prime onto this vector here. Okay, so this part here, more or less, is the extra part that is missing to R, big R compared to small r. Okay, so the phase R is small r minus this term here. Okay.
U is the unit vector.
U is the unit vector along the R, the small r line here. Okay. So if you do that, so U is equal to R over R. So if you do that, you can replace that in the expression of A, and you end up with this expression here. So you replace this term here. So A is mu 0 over 4 pi exponential ik small r over small r, and then you integrate all the sources times this phase term here over the full volume of current. Okay, so that's the first simplification that we can get. So what do we do with that now? Next step. You follow me? It's okay?
Yes. Green function.
No, not yet. Not keep it for the last part of the class. But it's behind. I mean, the green function is behind all that. Okay. Especially the retardation that I showed. Okay, so what is very important is that. Okay, so this theorem says that when the observation point R is outside the source volume, away from the source volume, okay, the knowledge of A, of the vector potential, of the retardated potential A, is sufficient to characterize all the fields that are emitted, that are radiated by the particles. Okay, so let's see if it's true. So if we know A, we know B from this simple relation by definition of A. Okay. What about E? So you use the last Maxwell equation. Here I consider monochromatic field. So the rotational of B. This term, we are outside the volume here, so there is no current. So I can eliminate that term. Minus, so the dE over dt gives you a I omega here, epsilon 0 mu 0, that's times E. Okay, that gives you this simple relation. E is I over omega frequency epsilon 0 mu 0 times the rotational of A. Okay, so you see that B and E can be expressed in terms of A. Simply, I mean simply. Okay, relatively simple.
It's a, okay.
Okay.
No, I wanted to say minus, but then I saw that the I put it up, like up.
Yeah, because of the I.
Yes.
When you reverse it.
Mm-hmm.
Okay, so so now we can calculate. I mean, we can develop this term here. Okay, using this formula. You remember that formula? Formula number 3. So let's consider a plane wave with vector k. So you know that when you apply this operator, okay, it's like multiplying by ik, okay. And when you use this one, so this one is the Laplacian, this is double, I mean, double time this operator, you get minus k2, okay. So you can apply this transformation when considering a plane wave, monochromatic plane wave. So I go fast, but this is this term here, the rotational of A gives you A, K, U, so U that's the direction vector here, rotational A, U rotational A. This term here, so that's for B. For E we need this term, so this term has this and that one. So this term gives you minus k square U, that's the first delta. The second delta here is A, is UA, you reverse the same. And that term here, the Laplacian, is minus k square A, okay? So you use this term, both from here and there, and you get the following. So B, B is IKU vectorial rotational A, U, yeah, rotational A. And E is I omega A perpendicular here. So how do I define this? This A perpendicular is A minus A scalar U times U, okay? And that's the transverse component of A relative to U. Okay, so you have U in that direction, A somewhere. So you have either the projection on U or you are the
Yes.
perpendicular component. Okay, so you see.
Right.
Okay.
So where these terms come from, you see here. You have.
It's like
you
the
have
shadow
A,
on
you have
the...
A and U. Here, so you have A minus U, AU. Okay, for the E field. So that gives you A minus AU, U here. And this is exactly the orthogonal component of A relative to the vector U.
So B and E are orthogonal to the propagation direction.
Yeah, that's one down. Okay.
You
So you have
We
K.
already know it.
Yeah, you have K vector, you have E vector, and B vector.
So U is the direction of K vector?
Yes.
Oh, some of them.
Now you're gonna say that the force is as well orthogonal.
Okay, is it clear? It's fine?
Yes. A break?
You still they want to break now? Okay.
No, I don't mind. I just need to be the stopper, but I don't care. No, it's my job to remember, but I don't have to.
Okay, so I mean, we reached our goal, which is to express the B field and the E field in terms of the retarded potential here, okay, in the simplest way possible. That's the case where we are looking far from the charges, okay, and with that we'll be able to calculate different things. Okay, so let's do that in 10 minutes after the break. Okay.
את כל הקורס הזה יש כמה שנים. לא, מה, אני למדתי סרט לפני שנתיים, לקח לי רגע.
וואו.
אני עדיין לא
גם מטורף.
סיכמנו פה את כל הקורס.
באמת? סדות זה עם אבא, נכון?
לא, זה...
למדתי מהר.
If there is any question, don't hesitate. Yeah? Any question? No?
Yeah, I studied this, but I forget, and you remind me, so...
Yes? So it's good.
Yeah, many years ago.
It refresh your mind.
Yeah.
כאילו שם לא מזדנים,
אבל זה לא פתוח, אז זה לא בעד זה.
פתוח. גג אבל.
יאללה.
מה היה? זה דבר סגור אבל. מה זה היה?
סתירה סיכרנו כבר.
וואלה, צריך מתחת לאף של ראש. כאילו, כועסת כבר למשהו. אבל בואי מסודר. מחמש את התקלת כאן, אנחנו צריכים לזה בזהירות, סבבה? לא, באמת. סתם לא.
לא, ליפול או שלא תשים לב.
לא.
Okay, so let's start over. Okay, so we saw this formula. As you mentioned here, you see that this is the structure actually of plane waves. Okay, with B, E, and K perpendicular one to the other. So that's a plane wave. Okay, it's not always like that actually. Okay, it depends on the medium in which you propagate. But here we are far from the scattering medium, so it's like a plane wave reaching that point. Okay, so what do we do with that? For instance, we can calculate the pointing vector. Okay, so the pointing vector, as the definition here, the pointing vector actually describes the power which is radiated away from the source. Okay, so this is actually the cross product of the E field and the B field of the H field here. Okay. So by definition, you can replace. So in this approximation, in the far field approximation, you can replace B and E by the expression that we found, and you get a pointing vector, which is given by this formula here, epsilon 0 c over 2 times E squared, modulus of E squared. Okay, so that's a very simple expression that gives you the pointing vector in terms of the E field. You can also define the radiated power.
Sorry, the vector pointing is
vector,
the direction of the power radiated?
That's the power radiated in a given direction. Okay, so we are looking in that direction U. Okay, towards some point. Okay, so from the source towards some point, the power which is radiated into that direction is given by the pointing vector. Okay. Remember that usually this is the cross product of the E field and the B field.
It's the big pi. Yeah? Why do you add the star in the H and the B?
You need because this is a number. Okay. So it's a number with just no. So it's not a number. It's a vector given by the direction of radiation, but the term itself. So this way you get rid of the time component. Exponential I am negative. You don't want. It's not something that oscillates over time. It's like integrated over time.
So it's like only the real part of H.
Yeah, at the end, it's here. Yeah, yeah, it's the real part here.
Okay.
ده بالنسبة لي زمان.
كده ده صح.
Yeah, I mean, it comes in calculation that removes actually the negative component. Okay, so that's in one direction. Okay. Now, if you want to measure the energy in a given solid angle, d omega around the direction u, so the power radiated in direction u in a solid angle d omega. Okay, so that's the flux of the pointing vector falling on the surface ds related to d omega. D omega is equal to ds over r squared. Okay, so this is called dp here. So dp is the flux of the pointing vector p times uds here. So p times u r squared dr. In the far field approximation, you can use the formula for the pointing vector, and dp over d omega gives you this expression here.
What is dp?
So dp over d omega, that's the power, the radiated power in a given solid angle.
Ah, p is the power. Okay, dp is the power.
Okay, so you have the pointing vector, that's the power in the given direction. Okay. Now, if you look at a solid angle, you look actually this is the flux the flux of the pointing vector through that surface.
We can say it's the flux of the power of the energy
The power is the flux of the pointing vector through the surface that you consider. So the pointing vector is not a power.
No, the pointing vector is not a
quantity is
power.
power.
It's the flux of the power.
Yeah.
Point-
Yeah.
Oh,
No,
vector
here,
pointing-
No,
here,
this is the power.
this is
No,
the power.
The
This is
equation.
the power.
No.
This is the power through a given small unit surface ds. And if you want to, and if you integrate over all the space, okay, then you get the total radiated power, which is the flux of the pointing vector on the sphere surrounding the scattering region. Okay. That's something that we will use, for instance, in the case of small particles. Okay, particles. If you are far from the particles, we can see that as a small particle. Okay, so that just to give you some way to apply what we have done until now. So that was we use this approximation, the far field approximation. Okay, there is another approximation. Seems to be very close, very similar, but it's different. The dipolar approximation, okay, which states actually that the region where you have the dipoles, okay, is very small, okay. So typically that L is very small compared to the wavelength, okay. So you have one dipole, two dipoles, small particle compared to the wavelength, okay. So if you assume, if you take this assumption, then you, instead of taking this second order here, you can just ignore it and replace exponential ikr over r, big R, by the small r, okay? And that simplifies.
L is the typical length of the
L
system?
is the size of the typical length of the volume of scatterers, of dipoles.
So how lambda is larger than
Because in that approximation L is very small. Okay, so like you have one or few particles. Okay, few
What?
atoms.
What's the meaning of U point R tag? I know what U means.
Yeah, so that was you remember
It's like
U.
the tiny piece, it's the same direction, right?
And the R prime, which is what the position of your scatter inside the volume V. Okay, so you project this vector onto the U vector. So that's the projection of R prime on U. Okay, that was from the. I go back if you want.
No, I remember what U means, but I don't understand the point.
The point?
No, like U point, the dot.
The dot
The
is
dot.
this is
Sorry.
scalar product. The
Ah,
dot
okay,
product.
okay. So,
Okay, that's the dot product between
Yes.
two vectors. So it's the cosine, if you want, it's cosine. It's R
but
prime.
it's at the same direction.
In
U and R tag.
U and
No, U and R tag are not in the same direction.
so you see U.
No,
The
U
direction.
and R
R
without
prime.
the tag.
Yeah.
Okay.
So that's U R prime is this projection.
Yes.
Okay. Okay, so if we do that, so if we simplify one step further, we forget about this term here because the volume is so small that R prime is very small compared to R. So we can replace here and obtain A of R, which is mu 0 over 4 pi exponential I k R. So we can take this out of the integral. Okay? And the integral is only on the current density J. Okay. You can, if you want, you can replace this integral by the time derivative of the dipole moment. So the integral of the current density is nothing else than the time derivative of the dipole moment of the source. I put the demonstration at the end of the presentation if you want to look at that later on the Moodle. Okay.
the connection between the dipolar moment to the
Yeah, so
current
so that's what I wrote at the very beginning, but the dipole moment here is actually equal, dp over dt is equal to this integral here. Okay?
No, the volume integral that equals to dp to dt, it's from the last lecture?
No. That's purely in this chapter.
Okay.
I mean, I can show you rapidly if you want. Where I moved to. So what do we have here? So the integral of j over this volume is it's not very clear. So j is the charge times the velocity times the position where the dipole, the charge is. So the integral actually reduces to the sum over all dipoles. Q is the charge of the dipole times its velocity, and velocity is d over dt. So that's by definition of the current. Actually, the current is the charge times the velocity. So that's the charge times the derivative of r, and qr is the dipole moment. So you get directly the relation. So from here, okay, so I just replace with the same equation, the same expression for A, for the retarded potential, just by replacing the integral by the derivative of P minus I omega P for a monochromatic wave. Okay, so if you use that, you can calculate the total radiated power by integrating over all the pi steradian, for the 4 pi steradian. Okay, so from this expression, from dp over d omega, here you integrate over all directions. So this is just a factor here, geometric factor, but the main term is here. Okay, so we end up with this expression for the radiative power in all directions, mu 0 times omega to the power 4, okay, over 12 pi c, times the dipole moment, modulus square of the dipole moment. Okay. So what is nice here is this dependence with omega. Okay. So for small particles, that means for wavelength much larger than the size of the particle, of the scattering centers, the power radiated goes as omega to the power 4, and that explains actually the fact that the sky is blue. So I will go back to that. I mean, that's something we'll show later. So for small value of omega, so for large value of lambda, actually, the radiation is less than for small values of lambda, large value of omega. So for small values of lambda, you have strong scattering in the blue. Okay, so small values of lambda, this is blue, going to red. So scattering is much stronger for the blue than for the red. So that's when you have direct light coming through the sky, the first thing to be scattered is the blue light. Okay, so that's what you see. You see the blue. Okay, because the particles in the sky are very small compared to the wavelength. Okay, when you are looking at sunset or sunrise, this is far from you, and it crosses a long distance, the atmosphere, a long distance. Okay, so the blue is eliminated, and the green, and you end up with the red actually. So what you see at the end, when the sun is far at the horizon, you see the red. So you see the sunset, the red light of the sunset. Okay, so actually this formula is important. The fact that the power radiated is proportional to omega to the power 4. So it's a very strong dependence on omega or lambda. Lambda goes as the opposite, so it's 1 over lambda to the power 4. Okay. So So that's the explanation of the blue sky. And then we can move to the second part. Okay? Maybe we finish soon. Don't worry. Okay. Okay, so the green function. Any question until now? So we have gone over this concept of retarded potentials, okay, that actually can describe how our dipole radiates electromagnetic waves. We can simplify actually the expression of the E field and the B field in terms of the retarded potential, okay. And in specific case, like if you are in the far field, or if you consider small particles, okay, then you have actually direct expression that tells you that gives you actually the field itself, and gives you information about the power radiated. So it's a tool, it's a useful tool to describe the scattering. Okay, the idea being that the light that is scattered by a particle actually excite the atoms, and the atoms re-emit the energy, okay, and that's what we calculate here. So the re-emission of the energy. Okay, so let me introduce this concept of green function. I will try to give you some feeling about what we mean by that. Why is it a very powerful tool, and what we can construct with that. So yes, this is one of the most powerful tool in the field of physics. It provides information about a system described by differential equation. So by definition, the green function is the solution of the wave equation with an initial source, okay, Dirac actually at a point at a given time. And that's how we are going to define it, but let me give you some intuition about that. So the question is why solving the green function problem is more interesting and more informative than just solving the wave equation and getting the solution for the E field and the B field. Okay? What do we gain here by addressing this question of finding the green function rather than solving the wave equation?
Finding the what?
So why is it more useful to solve the problem of the green function? So it's a problem of the wave equation with a source term, rather than solving the homogeneous wave equation with also a source term and finding the eigen solution, eigen mode, and all that. Okay. So to illustrate that, let's consider a game, a money game, for instance. Okay. You have a number of players, and there are rules, well-defined rules to play the game. Okay. But you don't know the rules, so you observe the game, but you don't know the rules, and you want to guess what are the rules of this game. Okay, so that's typically the idea of finding a solution to the wave equation. Okay, here's to finding the rules of the game. Okay, so the objective here, the observer has to guess the rules and predict what is going to happen. Okay, if you know the rules, so you know what will be the next step. Okay. So in the simple case, what you do is that you observe the game, okay, and for instance, you record the money each player has, okay, at a given time. So at different points, different players, okay, you measure the amount of money. So this is like measuring the wave function, okay. So that would be the solution of the wave equation.
It's the best intuition that someone gave us about the wave function, about
yes,
the wave function and the green function.
Yes, but you see, next step is even better. Okay. So now, what about the green function? Okay. Now, what if you ask the following question instead of how much each player has? You ask the question: is there a correlation between pairs of players? Okay. If a player play the game, is there a connection to the next one? I mean, are they connected? Do they play together? how do they interact, okay? And to test this interaction, you cannot answer this question by simply looking at each player individually, okay? What you need to know, what you need to do is to test the game, okay? And the way to test the game, for instance, is by doing the following. Everyone starts with 0 except one player, okay? So one player, player A, gets the amount of money M0, okay? All the other players, they don't have anything. And you look at each step, you watch how much of M0 is transferred from A to another player B, okay? So this way you look at the interaction, how two players actually are interacting with each other, okay? But you see, you put a source. You start from 0 and you put a source on one specific position, one specific player, and you see how this spread around to the next players, okay? So this is the most general information that is contained in the green function that tells you how players are correlated by pairs.
Green function is about communicating between.
Yes, it's the correlation. So yeah, if I made something here, what is the consequence on the other one there? Okay.
And the curl is equal to 0. Like there is no other source of money to make in this game.
What do you mean there is no other source?
There is no other source. I mean by okay, in the game you can earn money from the pile, not just by interaction with other players. Like,
yes, so that's part of the rules. Yeah, there may be some external.
Okay, so I just wanted to know if there are other sources, like in what you are trying to say, like when it comes to waves and not a monopoly.
So the idea to probe the green function, okay? The idea is actually to solve the wave equation with the source term. So that's the same idea here. You have the players, the game. Okay, you want to probe the rules of the game, but specifically you want to probe how you have interaction between players. You give to someone money.
Yeah, I understood.
Right, but yeah, I don't see other source of money coming in the picture. For the waves, yeah, you want the system has to be linear. Okay. It's a superposition of players of different sources. Okay. So you see that. So that's what is contained in the green function. The information contained in the wave function itself correspond to making A equal B. So you look only at one player. Okay. But if you look at pairs of players, then you get something more out of it. Okay. So that's just to give you some illustrations of feeling of what we are going to do. So the green function, how do we define it? The green function, so it can be scalar or tensorial, you will see that's technical. But the green function, G0 of R prime, you see 2 points, okay, at time t, is the solution of the Helmholtz equation measured at position R, with the source term at position R prime, position R prime, place at R prime, with the condition of outgoing wave, okay, because you have two solutions, either outgoing wave or incoming waves. So we take the solution of outgoing waves. So you are positioned at R, okay, and you have the source at R prime at time t, okay, and you want to see what you measure at position R. So the source term, which is described by this delta function, so that means that at t equals 0, you give the money, and you give it at position R equal R prime, okay? Because it's a Dirac, okay? It's a short spike source, okay? So it contains all temporal and spatial frequencies, okay? Temporal from this term and spatial from this term. All the k vector and all the omega, okay? So this way, actually, you probe the system fully thanks to this large spectrum. So yes, so all eigenmodes are excited because you are exciting all the frequencies and all the modes. all information is contained in the solution. That's the green function. Okay. So, but you have to probe all the pairs, all the R prime pairs. Okay. Okay, so we can
So like the time, okay, you said that all of the information are already in the green function, right?
Right.
So the answer for the position we have by R in the green, but what about the time, like the solution for the time in the green function? Is it by the frequency?
Yes.
Yes.
Yes. Yes. So at time t equals 0, you put your pulse, okay?
So okay, so we
you have all the frequencies, so you have a solution for all pair of position and for all frequencies. Okay, so let's be in the frequency domain, for instance. Okay, here, spectral gain function, so you can go to the frequency domain and consider only one particular frequency. So the green function are analyzed through that frequency component, G0 of R prime omega. Okay. So depending on the type of equation, okay, if you look at the scalar wave equation, so you have a scalar green function, which is solution of the scalar wave function with source term. And if you want to make it more complicated, you go to the vectorial wave function and you define a tensorial green function with the source term. Okay, now you can also go to the K space, so you can consider only one particular K vector. Okay, so if you solve it here for a particular K vector, you find that G0 of K omega is equal to 1 over K0 square of omega minus K square. So K0 is given here by omega over C. Okay, so that means that if K and omega coincide with the wave dispersion K of 0 of omega, then you see this term will goes to 0 and G0 will diverge. Okay, so that's typically a solution of the problem. That's exactly a mode solution of the problem. So we see that actually the imaginary part of G0 gives you the density of states. Okay, I will explain more that in future classes. Okay, but that's the way to do it. So you start from the green function, consider monochromatic waves of particular frequency omega and a particular K vector, and you get this simple expression for G, 1 over K square, K0 square minus K square. Okay, so how do you relate the green function and the field? Okay, that's the most important. So for, let's say for a particular point dipole, electric dipole at position R prime with the dipole moment P, so the field E of R, which is radiated from this dipole, can be written as E of R is mu0 over square times G times P, the dipole moment. Okay, so there is a simple relation between the field. Once you get G, you get the field, and you get the field information. Okay, so G is the green tensor. It's a second order tensor which characterizes the response of the medium, where the source is embedded. So you get the information actually about all the full system, including the source themselves. So the green function for any source, okay, you just, so instead of one dipole, consider a collection of dipoles, of sources, of emitters. Okay, so you just integrate again over the volume that include all the dipoles. Okay, and by the superposition principle, okay, it's just a sum. Okay, so E of R is I u0 omega times the green function times J, so to give R prime. Okay, so once known, green tensor allows to calculate the medium response to any source excitation, any object that scatter light. Okay, any question? Okay, the problem is that the green function is usually difficult to calculate. That's the problem. Okay, it's quite a complex function. I mean, the problem is complex, it's difficult. It can be solved numerically, but to have analytical expression for the green function is not simple. But there are particular cases, such as free space, okay, or homogeneous medium, where you can have analytic expression for the green function. So that's what we are going to finish with now. So just to remind you, we saw that the E field can be written as I omega A orthogonal, with this expression for A orthogonal as a function of P here, mu 0 over 4 pi exponential IKR over R, okay? Just to remind you what we found before. So let's try to calculate the green function now. So you remember that we had, actually we wrote this expression here to the first order here. When you have the zero order, the first order, that's what we wrote before. You can go further. So that's the expansion because of the far field. Okay, the further you are, the less these terms are important. So this is a second order term. You can push further the development. Okay. So if you replace, so that's R is R minus R prime, and so. And
is it like image charges, like the system with green?
I see what you mean. Yeah. See, there is. Yeah, that's possible.
But you know what I mean, like in general? You know, translate it.
Image particles.
Yes.
When you imagine in your solution another particle that is supposed to cancel something, השתמשנו בזה בחשמל, לא?
כן, בסדר. Image charges.
Yeah, you replace actually. You say that the field that you observe can be replaced by a particle that is a source for this.
Yes.
For this field.
Yes, image charges.
Okay, so that's. I mean, I'm not going into details. It's just boring. But the idea is that you can express. You can have an expression of the E field as a function. So this is the full expression of the field, and you can express it in terms of the. You can get from that the green function. Okay, we relate E and G before. Okay, so actually G, if you remember, we said that. Okay, that's the relation between E and the green function. Okay, so once we can write the full expression for E and the Taylor expansion of field. You can have a Taylor expansion for G here, so exponential AKR with 4 pi R in this term, which is the expansion here. The P, the dipole moment is factorized out. Okay, so that's the general expression. Okay, so then you can take or don't take the second order in the expansion. So if you simplify it, that's the green function in free space in the far field. Okay. So here you remember this is the projection in the direction transverse to U. Okay. So the field radiated by the dipole source is a spherical waves exponential IKR over 4 pi r. Okay, so that's a spherical wave corrected by a phase term, which is this exponential IQ UR prime. Okay, that's the fact that you have a delay. So that's the phase term, which takes into account the position of the dipole relative to the coordinate origin.
By I, you mean the matrix, or
yeah, that's
I don't
the
understand it.
identity. Yeah, the identity matrix. Okay. So in the far field, in the simplest case, actually, you see, you can take only the first term in the expansion. The simplest expression for the green function is given by the scalar green function here in free space in the far field. Okay, so again, you see that this is a spherical wave. So you have a source, okay, and in the far field, what you see actually is a spherical wave with the phase term here, which tells you the retardation between for the wave to come from the source to the position where you measure the field. So that's the general expression, the simplest, very simplest case for calculating the green function. I don't want to go further today on that. We'll use it in more specific case, more complicated case later.
This is the form of green function that we will use it?
That's the simplest way. That's the simplest expression. That means in the free space, so you are far from the scattering centers, from the dipoles, okay? But then you can use it actually. You can use it. For instance, we are going to consider multiple scattering. So the wave will bounce from one scattering to another, and we'll be able to accumulate in fact the effect of this. We'll have some kind of recursive green function that will be able to express the multiple scattering. Okay. You know that's very similar actually to the Huygens, you know the Huygens principle.
Which principle?
The Huygens principle.
Huygens?
Yeah, Huygens. Huygens said.
Huygens.
Yeah, so Huygens tells you that when you have a wavefront, you can imagine that each point of the wavefront is a new source that emits a spherical wave. Okay. So the next wavefront.
In the two-slit experiment.
For instance, yes.
Yes, example.
So the wavefront, each point is a source that emits a new spherical wave. All these spherical waves, they create a new wavefront, and then you can calculate actually the propagation of the wave from that. So that's actually using the free space green function to do that. Okay. So a lot of technical material today. Next time will be, I hope we'll be able to apply that in more specific case. Okay. I hope it was not too boring. I really wanted to give you some insights in these tools. Okay. So we have a kind of toolbox using either the retardated potential or using the green function. With that, we can stop. I think we have enough for today.
Thank you very much.
אם אתה לא תענה עכשיו טוב על השאלה, אז ימותו ילדים באפריקה. ואז הוא... ואז הוא שופט את הצד שלו.
So it's basically like a conditional probability matrix. Like
it's like, yeah, no, 2 points. Actually,
2 points or even more. Like if you have a sudden change in a specific point in the system, then you can know what happens to all the other points in the system, how it changes. So it's like
there is a very interesting concept that can be used in experiment, using instead of measuring the field, sometimes you cannot do that. For instance, you are on Earth, okay?
Yeah.
I mean, you cannot calculate the solution of the wave function in this system. It's very complex. It's big. It's huge. Okay.
Yes.
The way to do that actually is to measure the noise.
Noise.
At two different points. Okay.
And then you can
And then you can take many points like that. Okay. So they have like detectors, seismic detectors everywhere on the world. So they can actually measure. So the noise is like a source, if you want, a local source, and you measure the correlation. I mean the green function, which measures the correlation point by pairs of points. Okay. And they can reconstruct actually the system from that.
Wow, only from the noise.
Right.
Is this like how the Lego works? Lego.
No.
But it measures noise. Or like change.
No, it's not noise. They really measure the formation of the change.
But
So they can actually map the elastic properties of the Earth
wow.
by these multiple measurements.
I see. This is very.
I will put this paper. I have to find this paper. It's a concept, and it's not only for this particular experiment. But the idea is to explore the green function instead of having a source exciting the system, measuring the field everywhere. And by using the noise, actually, the noise is by itself like this delta R, delta T.
This is like the sudden change, the impulse.
Right.
Yeah. See, and then you like apply some kind of an operator that describes the system on the green function, you get the delta. Yeah. Wow. This could be. I mean, this is probably very convenient for a network theory, because it basically describes a network.
I have to find this paper again. It's not very good in details. And I will propose that for the final presentation. If you're interested, you can take it.
Yeah.
No, I mean, it's always very, very conceptual. This green function, we never really understand. But when you see this experiment, then you realize the importance of this 2-point measurement.
Wow. They never explained it. Like it was always an abstract object. Like
Yeah,
it didn't have any meaning. And now we see the meaning.
I hope so.
Yeah.
It's good.
Yeah. Thanks.